In this video, we'll be talking about how we can approximate areas. And we'll begin by looking at an example. Okay, so suppose we have this function, f of x is equal to x squared plus 2. I've graphed this on the xy coordinate plane. The scale for the x and y are not the same, and you'll see why I did that here as we go. But the idea here is we want to find the area. So we want to find the area between f of x and the x-axis on the interval 0 to 2. Okay, so what this is saying is we're starting at 0 here. We're going to 2, and we want to approximate the area of this region here. Okay. Oftentimes when we say we want the area between a function and the x-axis, we say that we want the area under the curve. So I'll be using this expression frequently. So at the moment, an estimation is the best that we're going to be able to do. And we'll see soon how we can get an exact value of this area. But for now, we're going to look at a few different ways that we can come up with a pretty good approximation. So what we want to do here is we're going to divide the interval. So our interval that we're talking about is 0 to 2. So we're going to divide the interval 0 to 2 into n equal subintervals. Okay, so n is just some value, and that whatever value we choose for n, that is just telling us how many sections we're going to divide this area into. Okay, so what we're going to do is we're going to divide this into some number of subintervals, and then once we do that, we're going to find individual areas and add them together. So I'm going to say that n is equal to 4 here. Okay, so I've divided that interval into 4 subintervals, and I'm going to label these. This is 0.5, this is 1, this is 1.5, and then 2. Okay, and what we do with these subintervals is, well, I'm going to draw rectangles. Okay, so I'm going from 0.5 up to the function value, and then here we're going to go from 1 over, okay, 1.5, and then at 2, like this. Okay, so we have 4 rectangles, and we know the width of each of these rectangles. The width here is 0.5. Okay, and then the height is, well, whatever the height is corresponds to the value of the function at the height of the rectangle. So right here, that distance right here is f of 0.5. Okay, this height right here is f of 1. This height is f of 1.5, and so on. And then this height is f of 2. Okay, so I'm going to label each of these rectangles. We have rectangle 1, 2, 3, and 4. Okay, so I think we have enough information in order to find an approximate area under the curve here. So we'll say the area is going to be equal to, so I'm just going to sum up the area of these 4 rectangles. So the first rectangle is 0.5 times f of 0.5 plus the width is 0.5 times f of 1. I don't want to use double parentheses, so f of 1 plus 0.5 times f of 1.5 plus 0.5 times f of 2. All right, so we're just going to calculate all of this and add everything together. Okay, so going through this basic arithmetic, we're going to get an area of 7.75. So a couple things to note here. First of all, this 7.75 is an overestimate of what the area actually is. And that makes sense because all of these rectangles have a little bit of space above the actual curve. Okay, so that 7.75 is an overestimate. The second thing that I want to mention here is that we have done what are called right-hand approximations. Okay, so sorry, I was just looking at my notes. So we have done right-hand approximations here. Okay, and these are called right-hand approximations because in each subinterval that we looked at, so from 0 to 0.5, that subinterval, we drew the height of the rectangle at the right-hand side of that subinterval. What we'll see is that we could have also drawn the rectangles with this height, which would be the left-hand side of the subinterval. We'll also see some where we draw the subinterval or the height in the middle of the subinterval, and those will just be called center approximations. Okay, so we've done this with right-hand approximations. That gave us an overestimate. Let's see what happens when we do left-hand approximations. Okay, so we have the same graph here. We have the same function. I'm still going to do n equals 4 subintervals. We want to find this area. So splitting this into 4 subintervals. Okay, this time we're going to do a left hand. Sometimes I can write left hand approximation. Okay, shorthand for this is going to be L sub 4. So that just means left hand approximation. We have 4 subintervals. So now the left portion of each of these intervals is where we're going to take the height of the rectangle. So here is our first rectangle. Okay. Here's our second rectangle. Here's our third rectangle. And here's our fourth rectangle. So we're going to find the area, or we're going to add the area of each of these rectangles. Okay, so to do this, we're going to say the area is approximately, so the width of each subinterval is still 0.5, or 1/2. And now we're going to say times f of our first height is going to be at 0, so f of 0, plus 1/2 times f of 0.5. Gosh, I don't want to write double parentheses. F of 1/2 plus 1/2 times f of 1. And then, so we did 0.5, 1, and then 1.5 is our fourth, the height of our fourth rectangle. So plus 1/2 times f of 1.5. Okay, so why don't you pause the video here and see if you can finish calculating this area. All right, so when we do this, we get 5.75, and this is going to be an underestimate. Okay, and again, hopefully that makes sense because our rectangles are leaving out all of this area that's under the curve. Okay, so the right-hand approximation for this particular function gave us an overestimate. The left-hand approximation for this function gave us an underestimate. Now let's do the center approximation and see what that gives us. Okay, so we're going to do a center approximation with n equals 4 subintervals, so we can write this as c sub 4. So splitting this up. Okay, so here, when I, in that first interval, 0 to 0.5, whatever the height of the rectangle is at the midpoint of that interval. So what is it going to be at 0.25? So my rectangle is going to look something like this. Okay, and then halfway between 0.5 and 1 is going to be the height of this second rectangle, and then we'll have something like this, and then something like this. So we can already see that this is going to be a much better approximation than either the left endpoint or the right endpoint, because each rectangle has a little bit of area above the curve and a little bit below. So it might seem like it'll kind of cancel itself out. So let's go ahead and find the area here. So we're going to say the area of these four triangles. So the width still of each subinterval is 1/2, and then times f of, well, we're going to evaluate the function at each midpoint of each subinterval. So our first midpoint is half of 0.5, or half of 1/2, which is 0.25, or 1/4, plus 1/2 times f of 0.75, or 3/4, plus 1/2 times f of 1.25, plus 1/2 times f of 1.75. Okay. So again, go ahead and pause the video and see if you can add this all up together. All right, so what I get is 6.625, and we see that this is in the middle of the other two approximations. So our left-hand approximation, we did that. Let me look at my notes. The left-hand approximation, we had 5.75. For the center approximation, we end up with 6.625, and then the right-hand approximation, we ended up with 7.75. Okay, so we don't yet know how to find the exact approximation of the area under the curve, or exact approximation. We don't know how to find the exact value of the area under the curve, but the actual area is 6.66 repeating. So this center approximation is actually, pretty good, depending on how close we want it to be to the actual area. But it's safe to say that the center approximation is the best of these approximations. And I should say that a center approximation is not always going to be the best approximation of these three. It happened to be the best approximation here because the function was always increasing. If we ever have a function that is exclusively decreasing over the interval we're looking at, the center approximation will also be the best. But if we have some function that is increasing and decreasing, something like this, and we're starting here to here, there's no way really of knowing right off the bat which of these approximations will be best. So it's helpful just to go through each of these and then compare it to the actual area to see which is best. Okay, so let's look at what we were doing here and what we could have done, or I guess the question is, how could we get a better approximation? How could we get these approximations to be closer to this actual area of 6.66 repeating? So one way to do this is to increase the number of subintervals. So right here, we were doing n equals 4 subintervals. Now if we were to still go between 0 and 2, if we were still looking at that overall interval for the function 0 to 2, but instead of breaking this up into 4 rectangles, suppose we split this up into 8 rectangles, or 10 rectangles or 50 rectangles. As we do that, we would see that the rectangles would be getting smaller and smaller, and the approximation would be getting closer to the actual area. And that's what we're going to be looking at next. So let's look at another function. F of x is equal to x minus 1 cubed plus 4. And we're going to look at that over the interval 0 to 2. And let's see what happens when we decrease the size of the subintervals, or in other words, increase the number of subintervals. Okay, so what we see here is f of x is graphed. We are looking at 4 subintervals, and those are left-hand intervals, right? Like here, this is the left side of this first interval. Okay, so what we have here is L sub 4. And if we were to actually go through and calculate the area of each of these triangles, this area is going to come up to 7.5. And then let's compare this this value, 7.5, to what happens when we go from 4 subintervals to 8 subintervals and then 32. All right, so this is 8 subintervals, and these are all left-hand intervals. So if we summed the value of all of these rectangles, this is going to come out to 7.75. Okay, and now we have 32 subintervals, and these are all left-hand subintervals. And if we calculated the area of all of these rectangles and added them together, we're going to get 7.9375. All right, so just looking at these 3 images, what we can see is, well, when we have 32 subintervals, there's just a little sliver in each of these rectangles that are below the curve. So each of those rectangles are not getting added to the area here. Here, when we have 8 subintervals, we have, bigger slivers that aren't getting added. And then when we have even fewer subintervals, we have some pretty big chunks here that are not getting added. Okay, so what we can see is as the number of subintervals increases, we're getting a better and better approximation. So we started at 7.5, and then we had 7.75, and then we had 7.9375. I don't know, maybe it's getting close to something around 8, but again, we don't know for certain. Now let's compare this to what happens when we take right-hand subintervals. Okay, so here are 4 right-hand subintervals, so R sub 4. And once again, the function here is f of x is equal to x minus 1 cubed plus 4. Okay, so when we do this with 4 right-hand subintervals, we end up with an approximate area of 8.5. Here, when we have 8 right-hand subintervals, we end up with an area of 8.25. And then lastly, when we have 32 right-hand intervals, we end up with an area of 8.0625. And again, we can see these rectangles here when we have 32 subintervals, we just have a little bit that's over the curve, and then when we have 8, we have bigger spaces that are over the curve, and then when we have 4, we have even bigger spaces that are over the curve. So again, we see that as the number of subintervals increases, seems like we're getting a better and better approximation of what the actual value of the area under the curve is. And so here is just a summary of what we've just done. So we had 4 subintervals, then 8, then 32, and we can see that the approximations are changing, whether we're on the left or the right side. And it looks like we're approaching, both of these seem like we're converging on the same value. And it looks like we're approaching on 8. And in fact, that is the actual area under the curve, is 8 for this particular function between 0 and 2. So we've gone through this approximation business. Ultimately, we want to get to the point where we don't need to go through all of this in order to get not just an approximation, but the actual area under the curve. And so this is going to be bringing together a few different ideas. One idea that we've been talking about is, how do we sum all of these rectangles together? Blah, 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 up to 31, 32. So we have 32 rectangles. We want to sum the area of all of those. And not just 32. Suppose we had 100 subintervals, or 1,000, or an infinite number of subintervals. What we'd want to do is, in order to sum a large number of things quickly, we're going to use sigma notation to do that. So that's one idea that we're getting towards. A second idea is a limit, right? We said that, as n, the n number of subintervals, as that is increasing, it seems like that is getting us better and better approximations of what the area is. So, if we take the limit here as n goes to infinity, where n is just the number of subintervals, that seems like that's going to get us to where we want to be. We want to get to the point where we are summing all of that area, and those rectangles are getting smaller and smaller and smaller, so that there is no leftover area that we're adding, or area that we are not adding, depending on whether we're using left-hand or right-hand rectangles. So let's try to generalize this idea of what happens when the number of subintervals increases to infinity. So suppose we have some function here. Let's try that again. So we have some function, and we want to look at it between a and b, so that's going to be our interval. And let's call this f of x. So what we want to do is we're going to take left-hand subintervals, and we don't know how many subintervals we're going to take, but since we're generalizing, we're going to take n subintervals here. Okay, so our first subinterval will be here. Okay, so let's call that rectangle 1, and then our second one will be here, and then our third one will be here, and so on and so forth. Okay, and then this one, this rectangle here, that will be n minus 1. If we're just counting, that'll be the n minus 1th. And then the last one, that'll be rectangle n. Okay, so let's talk about how we can find the area of each of these triangles. Well, rectangles. Our first rectangle, this position, let's call it x sub 0. It's just whatever that value is, and it's right on A. The next position is x sub 1, and then x sub 2, x sub 3, and then we're going up all the way to whatever our n value is. So this is x of n minus 3, x of n minus 2, and this one is x of, I have that backwards, hang on. I was counting too many here, so we're just going to look at this one. This value here is going to give us the height of the n minus 1 triangle, so this is going to be x of n minus 2, and then this right here is x of n minus 1. We don't need to look at that last position because it's the same height on both sides here. Okay, so what is the distance in between each of these subintervals? Well, how we could figure this out is if the entire interval is between a and b, that means that length is b minus a. And then what we're going to do is we're going to divide that into n subintervals. So dividing that by n. So that is our delta x. That's just the width of each rectangle. Okay, so one last thing we need to think about is, so we figured out the width of each rectangle. It's delta x. And then the height is just going to be whatever this is right here. So that point is on the function. So that height is just going to be f of x sub 0. This position right here, that will be f of x sub 1, and so on. Okay, until we get down to the height right here. This is going to be f of x n minus 2, f of x sub n minus 2, and then this height right here will be f of x n minus 1. Okay, so we have the height of all of these rectangles. We have the width. So all we have to do is we have to sum up all of those areas. So let's just go through it. So for our first rectangle, so for rectangle number 1, that's going to be delta x times f of x sub 0. The second triangle, the area of the second triangle is delta x times f of x sub 1. Okay, we'll also do the third triangle. I'm sorry, I keep saying triangle. Rectangle, delta x times f of x sub 2, and so on. And then when we get down to the n minus 1 rectangle, I'm going to say delta x times f of the height there is x n minus sub n minus 2, and then the nth rectangle, we're going to say delta x times f of x n minus 1 here. All right, so what we want to do is we actually want to add up all of these areas. That'll give us the area under the curve. So to sum all of these, we're going to use sigma notation. Our I value is 1, and we're going up to n. And what we want to say is, well, f of x I minus 1. Okay, so if I is 0 here, I'm sorry, if I is 1, that gives us x sub 0, and that's the first rectangle. If I is 2, 2 minus 1 is x sub 1, that gives us the height of the second rectangle. Okay, all the way up to n, we end at n when we have sigma notation. And when we do that, we'll have f of x n minus 1, which is what we have right here. So that will give us the height of each rectangle, and then we're going to multiply that by delta x. So that is a general way of how we can find the area under this rectangle. And this type of summation is called a Riemann sum. Riemann, let me write that more clearly. Riemann sum. So it's named after a 19th century mathematician who came up with this idea of how can we sum up all of these rectangles cleanly. Now, the one last piece here, we wanted to say, well, we want n to be going to infinity. We want to come up with the number of subintervals so that there is no area in between each rectangle and the curve. So the idea, in order to do this, is if we take the limit as n goes to infinity of this Riemann sum, that will give us an exact area under the curve. And that is ultimately what we've been trying to get to. So we're getting close to one of our big ideas, is how do we find the area under the curve. So we can take the limit of this sum. Again, it's going to be a little tedious if we have to go through all of this anytime we want to find the sum or the area under a curve, but we're getting there, and so we're almost to the point where we can apply some shortcuts, but the idea, even when we have the shortcuts, is still the same. We want to add up all of these rectangles, and those rectangles are getting smaller and smaller as the number of subintervals approaches infinity. So we'll finish this video off with an example. So we're given a function f of x is equal to 1 plus 1/10 x squared. We want to find the area of the rectangles. That will approximate the area under the curve in the interval 0 to 8. We're going to use C sub 4. This just means let's use center approximations, and we'll have 4 subintervals. So our curve will look something like this. There's f of x. We're between 0 and 8. Since we want 4 subintervals, we're going to go up to 8. Our subintervals will be at these positions. And then what we're doing is we're doing center approximations. So what that means is each halfway point of these subintervals is where we're going to have the height of the rectangle. All right, so we'll end up with that. And let's use a Riemann sum here to write this. So we're going to start at n equals 1, and we're going to go up to 4. And we have, thinking back, we want to know whatever the width of each subinterval is. That's going to be 2. And then we need to figure out what is the height. What's a general way that we can find the height of each of these rectangles? Well, in order to do that, let's see if we can come up with a pattern. So when n is 1, what is the height of that rectangle? Well, that's just f of 1 right here. So we'll say f of 1. When n is 2, in other words, when we have the second rectangle, we're going to say, well, what's the height there? That's 3. In our third rectangle, the height is 5. I was getting ahead of myself. When we're on our fourth rectangle, the height is 7. So is there a general way that we can write out what's happening in this right-hand column in terms of n? And what we see is that this 7 is 1 less than twice whatever the n value is. So 4 times 2 minus 1 gives us 7. 3 times 2 minus 1 gives us 5. 2 times 2 minus 1 gives us 3, and so on. So we could say this is f of 2n minus 1, and that'll give us the height of each of these rectangles. Okay, so this is a Riemann sum that is representing the sum of each of these rectangles. Okay, so let's expand this out. So this Riemann sum will be equal to 2 times 2 is the width of each of these rectangles. So f of 2n minus 1. So our first n value is 1, so f of 2 minus 1 is 1. So f of 1 here, and then we're going to have plus 2 times f of 3 plus 2 times f of 5 plus 2 times f of 7. I'm going to factor out a 2 from each of these. So I'm just going to add f of 1, f of 3, f of 5, and f of 7. So f of 1 is 1.1, f of 3 is 1.9, f of 5 is 3.5, f of 7 is 5.9, and then simple arithmetic from there, we end up with 24.8. And for comparison's sake, the actual area here is 25.066 repeating. So not too bad, and this is a lot, this is a lot cleaner or quicker than kind of getting to this Riemann sum saves us some time here.